So can you hear me, guys? It's Sabrina here. So when we're waiting for other people to join the meeting, I would like to do my land acknowledgement. Actually, it's first time in my life that I'm doing it, so I hope it will be okay. So I would like to acknowledge the lands where Women Health Research Institute operates, and we operate on traditional ancestral and unceded territory of Coast Salish people, Musqueam, Squamish, and Tsleil-Waututh people. So to make it personal, I recently took course about anti-Indigenous racism with PHSA, and it was very interesting for me to understand that we are in the 21st century. We moved so far ahead with technology and anything, and we're still talking about those, for me, weird things. And also, I'm a granddaughter of Holocaust survivors. So when I listen or read about something like this, I still don't believe that the things that happening with different nations and different people are still happening. So, and it's very sad. And I think we as people with research, we need to do our best to move our research in the right direction and do what we have possible to make our research equal and meaningful to all the people that live in British Columbia. Thank you. So I will start with the lecture. This is the second lecture within the Lunch and Learn series. And today I'm going to talk about statistics. So the title of my lecture is What is Stats? A series on unfortunate or fortunate events, a brief introduction into probability theory. So we talk a lot about statistics. We use this jargon, p-value, type 1 error, confident intervals. But with that time, I learned that people actually don't understand what it is and what it means. Yeah, like we using those inference analysis, descriptive analysis, but we actually don't understand the actual meaning of it. So I give one example. I started to study statistics by chance. I wasn't planning to do statistics, but I got into statistics. And actually my first year studying statistics, I didn't understand anything. I was lucky to have very good memory. I could memorize a lot of things. And basically all my first year exams, I passed just by learning and memorizing things. I didn't understand anything. And second year we took statistics. It was heavy course for like 12 credits, 8 credits theory and 4 credits lab. And suddenly in the middle of first semester, I'm looking on the board and I understood what statistics is. But I didn't understand what p-value is, confident interval mean. I understand the meaning of statistics, how what we have around us and what we see can be seen through the statistics. And since this moment, it was very easy for me, much easier for me to study. I still needed to study a lot, but it was kind of revelation. I suddenly understood what I'm studying. So I hope by this lecture, I can give you some hint or some basic part of statistics that will help you to understand statistical meaning of it. So the objective of this lecture basically to describe philosophical and principle and ethical applications that are in statistics, because we're doing research and everything we're doing, we need to do in the way that it's benefit people and that it's correct, that we're not implying something based on our personal decisions or based on our historical and educational background. We need to do a really good job. Also, I explained about 2 key concepts of statistics. It's probability and uncertainty, and how to understand the difference, because those 2 terms can be used interchangeably, and it's very important to understand what's the difference between them. So what is statistics? Basically, if you go to any of the dictionaries, you will see that it's a branch of mathematics. And basically, it's a science that using collected data to present the results. And because we're using statistics in different fields, in medicine, psychology, philosophy, social science, and other disciplines, it's very interchangeable and interdisciplinary fields that can be related to different fields. And all statistics is built based on two main principles. It's uncertainty and variation of the uncertainty that is determined by probability. We're all talking about probability theories. And generally, there are two types of statistics. It's descriptive statistics, when we describe data that we have without doing any assumptions or inferential analysis. And inferential analysis is basically our modeling. When we do the modeling, we try to understand how the sample or research we're doing can be applied to general population or to the population we're studying. So basically, statistics in general, it's describe your data and try to interpret your data the best way you can. So what is serious and unfortunate events? So I put here on my slide two pictures. Me as a baby born in Latvia, that is former Soviet Union. It's basically a totalitarian country. And my picture of today in Women Health Research Institute. So, and between them we have a line. So basically with the stars. Stars represent the event. So from me getting from Soviet Union to today day took some paths, and this path can be very different. It can go in different directions, depends on what choices I could make or what choices were made for me. For example, when I was born in Soviet Union, we believe that it's the best country in the world, the strongest country with the best economy and the best country to live in. So as a child, I couldn't believe that one day I could move to live in different countries because we lived under the Iron Curtains. So there is no way for you, like here in Canada, if you want to travel, we can travel. In Soviet Union, to get abroad, even to the countries of socialist countries like Poland and Czechoslovakia, Hungary, it was very hard. So when I was born, there was almost zero probability for me to end up in Canada. But what happened in 1985, Gorbachev came to power, and basically he led to collapse of Soviet Union, and suddenly the borders become open. So if I'm talking about the probability of collapse of Soviet Union when I was a child, the probability was very, very, very close to zero. There is always some kind of probability, but no one could even dream about this probability or this event happened. But eventually there was positive probability of this event happened. So I could move from Soviet Union to Israel and later to make decision to move to Canada, and based on my career choices to end up as senior statistician in Women Health Research Institute. So you can see under the stars that there is yes or no. So basically each event that happening in your life, it's event of choice. And if you look for three monotheistic religion, Christianity, Islam, and Judaism, actually most of those religions are built of the principle of choice. The choice that God gives to us, the choice that we as a people can take, or the choice and relationship between us and God. So, and for example, in Judaism, usually they talk about three main definitions of choice. And the choice can be random. So basically, we are not in power of the events that happening to us. We don't know what's going to happen. Our informal choice, the choice that can be made by us. What I'm going to drink today, coffee and tea. I have two choices, but I can make an informal decision of what I want to drink today. And there is also another type of choice that we don't have any control of it. It's the same example of collapse of Soviet Union. I couldn't choose it. No one can predict it basically, and it's happened. So it's not necessarily a random event because there was certain amount of events that lead to it, but this is the choice I couldn't affect in any way or change it. It just happened. So basically, and if you look on statistics, so basically all the religions as a philosophy maybe are built on the understanding what choice is. And statistics, basically, it's exactly the same. You have different choices, different types of uncertainties and probabilities. They can lead you from basically point A to point B. So, and as I mentioned before, statistics is very related to philosophy and to the ethics. And how? When we're doing any statistical analysis, we draw an inference. So we need to understand what the right inference is, or do we come to the right conclusion? Also, very philosophical issue is causality and correlation. Most of the models will do, like models that we have some significant results, will show what is correlation is. But correlation is not necessarily imply causation. Causation is where you have cause and effect, and you know exactly in which way your cause affects in your effect. And we also need to understand how to make the right conclusion. We got some results, but we need to understand what conclusion we can make based on those results. And there is, in statistics, there are also ethics implication. For example, there's two main organizations in North America. It's American Statistical Association and Statistical Society of Canada. And if you go to their first page, they talk about ethics in statistical research. So, and what they mean for you, if you're a statistician, you need to be sure about integrity of your data and methods. You take, like I as statistician should take personal responsibility and accountability of the things I am presenting and model I'm doing. So my work and results should be definitely unbiased. It's my responsibilities as to the clients, team members, and stockholders. So I need to do the best job I can to help them to lead their research. And any research I do, and I mentioned it is my land acknowledgement, any research I do, I'm responsible for the society. How the results I got will affect society and where they lead. So now we come to statistics. So there is two main concepts in our life. We have natural variability of the events and uncertainty. So on my slide, you can, this is very famous picture, probably every statistical lecture they put in it, it's natural variability. So giraffe in the beginning of its existence was relatively short, but after that, by trying to reach high and high leaves on high and high trees, the neck of the giraffe grew. So means the giraffe changed from situation A to situation B by natural changes of the events and natural variability from short neck to long neck. But there is also uncertainty. What is uncertainty? Uncertainty, it's lack of precise knowledge. We know about something, but we don't know exactly what it is. And this and uncertainty usually arising from randomness in nature or incomplete information. And the other picture of my presentation, it's dice. We throw in the dice, we get into results on the dice in random. We don't have any idea what we're going to do. So this is uncertainty because we cannot predict what we're going to get. Also, uncertainty is very related to medicine. I put here a citation from William Osler. I understood that he's a father of Canadian medicine. So he actually used uncertainty in this citation, and he said, medicine is a science of uncertainty and an art of probability. So basically in medicine, what is uncertainty? Uncertainty in medicine, it's we don't know everything about the patient. We don't know everything about environment, about the disease. We only have information that we have in the patient chart or the family or patient showed us or give us. But what is the probabilities? Medicine probability, it's actually risk-adapted algorithm. When a physician trying to make diagnostic and therapeutic decisions based on reducing the uncertainty. So as more and more information the doctor gets in about the patient by tests, by different procedures, the more information the doctor will have, and he or she can make more informal decision about the patient's course of treatment. So statistics everywhere, as I said, statistics is an interdisciplinary field, and here, based on this citation, we can see the statistic can be applied to medicine as well. So what is uncertainty? Uncertainty is usually incomplete information or disagreement about something we know. So it basically can be error in our measures, our missing data and stuff like this. So you can see here that someone threw the arrow in this circle. So the first picture is actually a measure of uncertainty, because we all wanted to hit the middle of the circle, but because of our skills, we can get different results. So you can see that all other X's on this picture are kind of in random. But we also can have a bias measure. On the circle on the right, you can see that maybe our arrow was done wrongly or something happens, that all the X's come in the same point on the right. So this is a bias measure. So basically, we can have an uncertainty is a random error and something that we cannot measure, or by doing something wrongly, we can get a systematic error. Also, the uncertainty, it's inherited unpredictability of acknowledgeable true value. So it's randomness. So you can see lottery tickets, same as the dice. You can 649. You can get any 6 out of 49 numbers with specific probability depending on number of people participating in this lottery. So this is basically different examples of uncertainty in our life. So what is uncertainty statistics? Actually, there are different types of uncertainty that can be identified and known. And if you look on those three first terms, epistemic uncertainty, aleatoric uncertainty, and ontological uncertainty, all those terms actually comes from philosophy. Yeah. So it shows that how statistics actually is a part of philosophical field, probably, because you can explain some of the ways uncertainty affecting our lives through those philosophical terms. So what is epistemic uncertainty? This is things we do not know as a result of our experience and data. So when we're doing research, we have specific data. We need to do some assumptions, some proxies. We don't have all the information, and this gives us epistemic uncertainty. Uncertainty is that we don't know what to do with it. What is aleatoric uncertainty? It's something unknown or random, so there is nothing we can do about it. It's just natural phenomena that can happen. And there is also other type of uncertainty that this is important. It's unconscious utilization and incorporation of methods. So basically, we are in charge of this type of uncertainty because based on our belief system, based on our understanding of system, and based on our vision of the world, we can do some assumption or lead our research in the way we think is better to lead it. And basically, there is additional type of uncertainty on this slide, like IQ cycle. It's different methods and parameterization and descriptions that usually used in engineering mostly. But if we look on the three main types of uncertainty, we understand that there is something we can work on to improve and reduce, and there is something there is nothing we can do about as aleatoric uncertainty. So the examples of epistemic uncertainty is basically our data preprocessing, our parameters that we defined, methods that we decide to choose, how we structure our models, what algorithm are using, how we interpret results of our modeling. So this is type of uncertainty that we are in charge on. For example, if we have longitudinal data, but we apply methods that are applicable for cross-sectional analysis, yeah, we will introduce an error in our calculation in our model, and we present wrong result just because we choose not appropriate method. Or when with the technology going farther away, there is more and more algorithms that can probably give you like better results, but we not always have monetary means to apply all those algorithms. So we need to compromise. So basically we need to choose best algorithm possible within the means we have. And also there is issue of interpolation, is missingness of the data. When we have the missing data, do we want to exclude the missing data and reduce our sample size that may affect our calculation, or we decide to impute the missing data using different techniques, but would this missingness imputation will affect and bias our results? We need to check and understand what we're doing. So basically, the most classical understanding of uncertainty in statistics is aleatory uncertainty. So this is the measures we take, and this is the sampling. So when we do analysis, we never can do analysis of full population. We usually have some population that is self-selected, and we decide sample from the population, but our sampling will introduce the random uncertainty. Also, the input variables that we get into the model and our output variables from the model, we cannot determine those variables with absolute precision. So there always will be error in our measurement. And additional to this one, there's two additional terms that use in statistics. It's homoscedastic and heteroscedastic. So basically, when we're talking about statistics, we usually talk about mean and variance. And if our variance is stable and not changing over the time, it will be homoscedastic relationship. And if our variance is changed, it's heteroscedastic relationship. And based on those relationships, it's basically how we can make inference between our models and what we want to, and the results of our research. So what is homoscedastic uncertainty? It's expected value of empirical mean in a given data, and this expected value of empirical mean, it's constant. And each point basically we have is basically linear regression. We have line with dots of our measures around the line, but the difference between those dots and the linear regression mean line is usually constant. When we're talking about longitudinal models, where there is two parameters, it's mean and variance. So in longitudinal models, we usually have relationship between groups we want to compare. This will be our mean comparison between groups, but the variance will not be constant over the time, because in heteroscedastic relationship, we're also looking on interpersonal variability. The events that happen into same person over the time are related to each other. So this is basically the main terminology for aleatory, and it's kind of theoretical uncertainty. How we can deal with uncertainty? It's why statistics, it's not actually like core science like mathematics, because we only can reduce uncertainty by doing better model and by collecting more information and using better sample size. But we never will be able to change or improve aleatory uncertainty, because it's coming from the nature of things and it's coming from the randomness of things. So there is nothing we can do about it. And here there is a picture. We usually, unless we are census, we don't do analysis on full population. So we sample from the population. And if we do like best protocols ever, and think about our algorithms, how we're going to sample and what we're going to do to get representative sample. It's still a sample, so we only can imply and get our results from the sample, and after that we need to think how the results we got from our sample can be inferred to the general population, and if it's possible. For some models it's possible, for some models we cannot do anything, and we need to say that those are results only good and valid for the sample we chosen. And if we're going to calculate our average and statistical measure like average invariance for population and sample, they always will be different. And for example, one of the way to work on this uncertainty is do bootstrapping, to basically resample multiple samples from the same size from the population. But if we, in general, if you have really large sample, like for example, we resampled 1,000 samples from our population. In general, because our overall sample size now is much higher, 1,000 times more, if you look for each specific sample we bootstrapped, the average invariance and other statistical measures in each sample will be different. And this is our uncertainty, because whatever we sample, every time we sample, we get different results, and basically there is nothing we can do about it. So I can summarize it that no matter what you do, no matter how you sample, you try and improve your procedures, you do your best, there is still uncertainty. And in our future lectures, I'm going to explain what are the actual statistical measures and how we can explain it when we're presenting our research. Now we talk about uncertainty and we go into the probability. So this is another very famous citation about statistics. The most important questions of life are indeed, for the most part, really only problems of probability. And this is what I talked during my first slide, talking about my life, that anything has happened in our life have some kind of probability we don't know about. And this is very simple example. For example, I left my house, I looked on the roof of my neighbor, that his roof is really wet. So I said, oh, interesting, it probably was rainy, so my roof, the roof of my house will be wet as well. But it's not necessarily true, because maybe my neighbor woke up in the morning and decided to wash his roof. So this way his roof will be wet and mine not. But I cannot know about it if I didn't look on my roof. So my assumption is that my roof will be wet because I'm pretty sure it was rain, and my probability and the probability of roof being wet based on my perception of the situation is 100%. But my neighbor that sees my roof that was not washed, he understands this probability differently. So everything we go, there is a probability. It can be zero sometimes, but usually it's not. So what is a probability? Probability defines as the likelihood of occurrence of an event. So any event in our life, any event around us will have a likelihood of occurrence. And simple calculations, this is probability you probably all studied at school. It's basically divide number of favorable events by total possibilities. And if we looking for probability, there's multiple probabilities. One of the probabilities is classical theoretical probability. There is empirical or experimental probability and subjective probability. So as the example I give about the wet roof, it's actually subjective probability, because whatever I saw and whatever my neighbor saw, it's two different things. So what is the classical probability? It's the probability we study at school. We use the coin head tail, we're throwing it out, and there is 50-50 chance to get something. So this is our classical probability. So additional example is rolling a die, or by rolling a die, we get the same probability of 1/6 to get each side of the rolling the die. Or we selecting the bingo balls. Yeah, for each bingo number of our cards, there is equal probability to be chosen. Or assuming we don't have any knowledge, we get in a test and we need to choose out of 4 multiple choices. If we don't have any predominant knowledge of what we're doing, we will select our choice of answers in random. There is also empirical probability that is bits different. So what is empirical probability? It's likelihood of events occurring based on historical data. If on previous slide we didn't have any information about the dice, it's purely in random, here we can use historical and collected data to do some prediction or calculate the probability. Basically, additional name for empirical probability is relative frequencies. So how this probability is defined? It's a value gained from performing an experiment. So basically, if we roll in the dice 200 times and we wanted to get 6, and we got 6 and 30 rolls of the dice, our empirical probability will be 30 divided by 200 experiments. So where usually empirical probability used, it's the probability we use in research mostly. So we can calculate probability or prevalence of specific side effects in clinical trials. We can predict weather in June based on looking on historical data of rainy Junes in last 10 years. And we can predict how the stock exchange going to behave the next day using like moving average or some other historical information that we know. So here on the slide, I actually give an example, the difference between the theoretical and empirical probability based on the dice roll. So if we have a dice and we want to look on the probability of getting odd numbers, it will be 3 divided by 6, because we have 1. For odd numbers, we have 2, 4, and 6. But if you look into the same problems through the lens of empirical probability, and we had our experiment done 200 times, odd numbers, for example, appeared 140 times. So this way, our probability will be 140 divided by 200, so it's 7/10. So theoretical probability, empirical probability will give us different results, because this is those are different types of probabilities. Additional interesting things about probability theory is axiomatic probability. So basically, your classical and empirical probability are parts of axiomatic probability. And all probability theory is based on generally 3 axioms. So axioms were developed by Kolmogorov. For example, if you do test for normality, usually we'll see Kolmogorov-Smirnov value that will show if your results are, or your distribution is normal. And this is the same guy that actually developed all those axioms in statistics. And he actually said that because statistics is part of mathematics, it's very important that it will be built based on the axioms, exactly the same way as other parts of mathematics, such as geometry or algebra, are done. And here we come into the probability theory and basic 3 axioms of mathematical probability. there is probability for every event, and this probability will be either 0 or positive. There is no negative probability. If you look, on sample, basically on all the events you can get out of experiment, for example, you're recording all the results of the dice roll, total probability of all outcome possible will be 1, so probability cannot be more than 1. And also, if in your sample you have 2 mutually exclusive events A and B, so your probability of event A and B, mutually exclusive events, will be sum of those probabilities. This is all. Basically, whatever we have in statistics, whatever we calculate in statistics, it always will be based on those 3 axioms, and it's very important to understand them. In addition to theoretical and experimental probabilities, there is Bayesian probability. We all talk in our real life in the research about predictive modeling, Bayesian probability, Bayesian modeling. So this is basically type of probability. And how it's different from other probability types, it's that we can predict something based on additional information that we can get. If for experimental probability, we're looking only on historical data, here we can adjust our model or change our understanding of the model based on the information we just received. And this is where I want to give an example how our decision using probability theory can change based on the new information we have. Assuming we want to bet, like now, if you look on Sportsnet or all those sports events, all the ads between the games, it's about betting on something. So assuming we decided to bet on athletic championship, and we have 2 athletes that we think they have good chance to win, and we're making a decision who we want to bet on. So assuming out of 4 championship, N won 3 times and J won only 1 time. So if I want to bet today or who's going to win the next championship, the better chances are probably for N. But I have additional information to it. I know that J won when it was very rainy, and athlete N won only once out of, like, not every championship that N participated had rain. So now, because J won only 1 championship that he ran under the bad weather condition and he won, I think, oh, maybe now, if I know that there is rain tomorrow, J going to win. So now I have additional information about my athlete, and I also might have additional information on the weather condition that will be during the next race, and this way I can adjust my bet. So here, basically, I show it in the picture. The yellow circus is it's our sample. It's our sample space when we have all possible events. The blue stars are N and red star is J. And now if I want to look on actual probability of winning, N won 3 out of 4 and J won 1 out of 4. This is their probability. And I can see that based on a statistical probability theory axioms, the probability of N and J winning the championship, it's 1. So on the right, I'm writing, yeah, both N and J have probability more than 1. So it's good. My total probability is 1 is good. And those events for J or N winning the championship are mutually exclusive. The node depends between each other. And basically, we have 3 hypotheses here based on this simple example. We have the hypothesis that there's a higher chance for N to win next competition, and we accept this hypothesis because probability of N winning the championship now is 75 and J only 25. There is a low chance for N to win competition. We reject this hypothesis based on the same reason, and we reject probability of them having the same probability. Now we introduce the new information to this problem, and we say, oh, but we know that there is 50% chance that there will be rain during the competition. And we know that it rained twice when N won the competition, and only once when J won the competition. So now, in addition to calculating the probability of winning the next event, we introduce in something that's called conditional probability. So what will be probability of each athlete to win the championship, condition to knowing that it will be the rainy day. And here the situation will change. So here I basically do example of basic conditional probability. We have two events, A and B, and those events are in the blue area in the middle. It's where events in interchange. So what is conditional probability of A knowing something happened as B? It will be blue area divided to A red area and blue area together. And what is conditional probability of B? So it will be opposite. And this is, I don't know if you need to remember it, but basically below is the main formula that used in probability theory as conditional probability. What is probability of B conditionally to A, and what is probability of A conditionally to B? So now let's apply to our example of competition rain. So white circle is our competition and who win, and the red circle is getting rain during the competition. We know that both J and N won once during the race. It's why I put them in the blue circle. So we know that probability of J winning the competition is 0.25. And we also know that probability of rain is 0.5. So the probability, and we know that probability of winning the competition for N, it was 0.75. Now, when we apply a conditional probability formula on it, we understand that probability of J winning where it was rainy is 1, and probability of N winning where it was rain at 0.67. So knowing this information, we change our bet strategy. When we didn't know anything about the rain during the competition, we definitely would be betting on N, but now we can see that J has much more chances to win under the rain, and we're probably going to put our money on J this time. So basically, this is very simple example how the historical information can predict the results, and also how by introducing the new information to the equation, our decision might be changing. Also, as I talked before, there's additional part of probability, it's subjective probability. So it's probability that's related directly to what's happening to us, based on our personal experience and our own judgment. Yeah, and I put here some examples from the literature and found, but additional example, for example, now Fed's changing the prime rate for our mortgage. Yeah, every beginning of the month we are waiting for Fed to make the decision if the interest rate is going to be stable, go up and go down. And we don't know what the Feds are going to do next month, but based on our historical information, based on our preference, for example, I like variable rates on my mortgage. Someone prefer fixed rate because it's more stable and more predictable. But based on our knowledge of information, based on our personal preference about our rates, we can make different decisions of what to do, how to close our next mortgage. So also, I often laugh, for example, when someone comes to me and say, oh, Sabrina, I have this excellent financial analyst that can help you to trade stocks. But I said, no, I don't believe that any analyst is excellent. Why? Because there is 50-50 chance for stock is a go up and down. So basically, who is your best investor or best financial analyst? It's probably the person that had a lot of knowledge and had a lot of personal experience to predict where the stock is going to go. So it's very subjective. The same, like one analyst can say, like, I read a lot in Economist and Globe and Mail, and there is a lot of economic articles or pieces. One say, oh, we are heading to recession. Another say, oh, it will be mild recession. And another one say, oh, it will be not recession. But all those people predict the future of what happening with recession based on the data information they have and based on their beliefs and their understanding on situation. So that it's part of probability. Something might happen, but this probability will be subjective based on person belief and understanding of situation. So here I want to do summary about what we talk in like general term, because one of the objective was to understand what is probability and what is uncertainty. So what is probability? There is no one way of definition of probability, and I showed you there's different types of probability. Meaning of probability is usually interchangeable and can be used for both random variation and our personal uncertainty about the things. Probability is accompanied on how we describe the future. So we have some information, we want to predict the future, and we using the models and information that we have to predict something that might happen. And probability, as I showed an example with the athletes running in rain, probability is not stagnant. Probability can change with any change in the system we introduce. Yeah, in the minute some piece of information change, our results and inference we getting from the results might be different. And what is certain that probability is measuring the randomness of events. We don't know what's going to happen because there is some aspect of randomness in each event happening. What is uncertainty? Uncertainty is all about the present and how much presently we know about the past. So if probability is talking about the future and predicting in future, uncertainty it's the information we have about the past and we have presently, and there's not much we can do about. Uncertainty can change with gain or loss of knowledge, as I explained. If we get more variables to add to our model to explain something, we reduce uncertainty because we have more information. Or we change our outcome definition. We consult with our co-workers and we decided to do different model that may be better modeling based on the data and type of analysis we want to do. So certainty can change. And what uncertainty actually means, it's lack of precise knowledge. And in statistics, what statistics is trying to do using probability theory, it's basically, we always trying to quantify the uncertainty. We cannot reduce it, but by using proper tools and knowledge, we can quantify it, we can present it, and we can explain our results knowing what our uncertainty is. So this is the end for our lecture. I hope it helped you to understand a little bit more about like general terms of statistics. And next lecture, I think, will be not lecture done by me. It will be related to knowledge transition. But after that, I will be planning to talk about what we talked today in more details. We're going to talk about density distribution and different statistical measures. Thank you. Are there any questions? No questions?
I have a question, Sabina. I loved your graphics. So testing for, bias at random versus systematic bias. So the two circles you showed with, all the pluses in congregated in one area versus randomly spread apart. Can you say something about are those two separate tests, or is there a single statistical test that you would use to assess for those two different kinds of bias?
No, there is no different test, because when we do what is bias? Bias is actually uncertainty. When we're doing the modeling, we need to see what uncertainty we have. We can identify it based on results. I usually do it graphically. Like first, before I don't do any tests come later, and there is very specific tests for each of the distributions, and they're known for, like, we using same test over and over again, and we're all familiar with it. But I think in order for you to proceed to the part of doing analysis, I do a lot of visualization. I do a lot of box plots. I do a lot of kernel density distribution, scatter plots, trying to see my data, because this is going to give you bias. An example I can give you, you remember one of the grants that for the last round of grants, I think it's Prime Grant. What was the name of the grant? I forgot.
Yeah.
So the ones that related to ultrasound, they actually got the money. They come to me for like help them to write the method section for the grant, and they show me several papers. And when ultrasound was measured, and it basically angle of the ultrasound, when it was measured, all the papers presented it in linear relationship. But actually, if you look on scatter plot in one of the papers, you can see that there is no way there is linear relationship, because if you build the line, it will be straight line. There is no intercept. Your intercept is basically zero. Why? Because the distribution of any angle mathematically, it's usually circle distribution. So if you change the analysis of your, so basically by looking on it as a linear distribution, we introduce a lot of bias. Yeah, because dots around our line will be all over the place. In the minute you put circle around it, it will be random, because they all will be within the circle, and circle can go both ways, from 1 to 680 or minus 180. Yeah, it's not only depends which measure we have, it also depends which way we're going to go. So this one of the way, by if I have the data and visualize it, I could see, even without knowing anything about ultrasound, I could see that probably it will not be linear distribution, and this is one of the way for me to remove the bias from my future modeling.
Yeah.
Specific.
So that's something we all should be doing, before anyone comes to you to do data analysis, is that kind of visual, like just a scatter of all of their raw data to look at the distributions of the data set that they have before you. Yeah. I mean, I'm sure you do the same kind of visualization on your own anyways, but just to give, whether it's a trainee or a researcher, a better sense of the data they actually have before they come to you for analysis.
Yeah, they can do it. And I think as a statistician, we talked in the beginning about ethics. Yeah, it's my ethical responsibility to give you the best results possible, taking uncertainty in sampling and modeling that I can perform on my computer. Yeah, but I think if you come into me, you need to understand and know your data. Yeah. Because this way we also can have meaningful conversation about what statistical methods we going to apply. And also this first step of data visualization or simple descriptive without introducing any statistics, it can help us in the future understand our results better. For example, another example I can give, actually was asked about it in one of the interviews I did. So you have simple analysis, age and gender that were not statistically significant in univariate modeling, like gender against outcome and sex against outcome. But when sex and age were put in the model, suddenly they become significant. Yeah. Why? Because it can be possibility. So this is the simple interaction. So probably, for example, all your male in the sample were older than female. So in the middle, in the minute you put two of them in the model, you will have like different results. It becomes significant, and you need to understand why. Yeah. So, but if you performed simple visualization and descriptive analysis before going to the modeling, you already would know about it. You will see the difference, how the age and sex are distributed in your sample, and you understand right away that you probably either need to do stratified modeling by sex, or you need to incorporate the interaction terms of your model. Yeah, it's very important to understand your data, even if you're not statistician and you're not going to do analysis yourself. You need to know what you have. And it's related to my previous lecture about data. Yeah, when you do data visualization, you also understand what quality of data you have, if you have a lot of outliers and everything. So it's a very important step, and it can be done in any software, probably even in Excel. You can put some scatter plots. Yeah.
Does anyone have any more questions for Sabrina? Everyone is sufficiently fulfilled from an educational standpoint, Sabrina.
I guess so. Yeah.
And we love the
statistics are fascinating. No, I never saw the statistic. And actually, when I'm preparing, each time I'm preparing those lectures, I learn more and more things, not about I didn't know about it, but I kind of learn it from different perspectives. So it's very fulfilling and interesting, I think.
the way that you teach is fantastic.
No, my accent probably destroys half of it, but there is nothing I can do about.
It's great. And I'm going to have big shoes to fill, because I'm up next, folks. Next month's Lunch and Learn in July is knowledge mobilization basics. So just a quick note that we're back to regular programming. So I believe the date is July 12th. So that's second Wednesday of the month, from 12 to 1. And we will just stay tuned on our social media channels. We're going to be doing some Ask Me Anything and polls to just get a sense of what folks might be really interested in hearing around knowledge mobilization. So planning versus terminology, or certain aspects within planning, or integrated KT. So would love your feedback there. And thank you, Sabrina, for these two amazing presentations. We, if you're keen to continue this, I'm positive that you'll have a captive audience for a third and fourth round. So yeah, thanks everyone. And thanks, Sabrina.
Yeah, and if you have questions, specific questions, send me, because as we agreed, we're doing series of newsletters. If there is something specific and interesting, I might do short newsletter, or short like sample, so everyone can see. Yeah, just let me know. Thanks.
Yeah, your question might be the same question that other people have, so feel free to send it over, and Sabrina can answer those, and we'll share them via our eBlast and social and all those things.
Okay, thanks. Bye.